Welcome back. In topic 6, we will use semi-differential control volume to derive heat equations for internal flow convection. Let's first review those heat equations that we studied in basic convection. This is the flow chart for the heat equations. Generally speaking, there are two categories of heat equations. Category number 1, heat equations 1, 2, and 3. They do not depend upon the thermal boundary conditions. Therefore, they're valid at any condition. Category number 2, the heat equation will depend upon the thermal boundary conditions. Comparatively, students are familiar with equation 1, 2, and 3 because they have been using them for a while. Therefore, our new goal in this section is to derive the temperature profile and convection heat rate equations under different thermal boundary conditions in order to help students to understand where this equation coming from and under what conditions. B. Let's revisit temperature profile and mean flow temperature. First, as presented in equation 1 and the plot, the flow temperature inside the tube is changing in both R direction and flow X direction. On the other hand, the mean flow temperature is averaged over the cross-section area. Therefore, it is only a function of X. This averaged property is very useful for engineering applications. For example, if we know the water mass flow rate, mean temperature at the inlet and outlet, immediately we can estimate how much heat is needed from the external flow. Therefore, in all the heat equations, we use mean flow temperature rather than flow temperature. C. Now we're ready to derive mean temperature profile. This is our finite tube system with outside diameter, inside diameter, mean temperature at inlet, mass flow rate, heat transfer coefficient, thermal conductivity of the tube wall lengths, and mean temperature at outlet. 1. Here is the fact. After the flow temperature is averaged over the X direction, all the physical variables, if they change, they only change in the X direction. Therefore, this provides us the foundation to define the semi-differential control volume, which has no energy generation inside, and it is at the steady state. 3. We can identify all the heat transfer mode for our defined semi-differential control volume, which is mass flow carried the enthalpy in and out. Convection is into the control volume from the side surface. 4. Now we can apply the first law to the control volume. Energy in equal energy out. Cancel this two term. Equation 1 become equation 2, which is available for all the thermal boundary conditions. However, the mathematical expression for the convection heat rate will depend upon the thermal boundary conditions. First, if the thermal boundary conditions is constant heat flux, the convection rate is best represented by the heat flux times the side surface area. Second, if the thermal boundary condition is constant surface temperature, the convection heat rate is best represented by heat transfer coefficient times the temperature difference times the side surface area. Third, if the thermal boundary conditions is constant external flow temperature, the convection heat rate is best represented by the temperature difference times the differential distance dx divided by the total thermal resistance, which is defined in equation 3.4. It is a summation of internal convection thermal resistance plus the conduction thermal resistance in the tube wall plus the convection thermal resistance outside the tube. This is the thermal circuit, shows how they're related. They're in series. D. We will use example 6 to show how to do the derivation on the mean temperature profile for constant surface temperature thermal boundary condition. From previous slide, we have equation 2 and equation 3.2. 5. We make equation 2 and 3.2 equal to yield equation 4.1, and then separate variable dTm and dTx. 6. We integrate equation 4.2 by combining the boundary condition into the integral to yield equation 5.1. By plug in Tmi and Tmx into the natural log, it yields the left hand side equation 5.2. The right hand side, by using The definition for the average heat transfer coefficient Hx bar, it yields equation 5.3. Next, make left-hand side equals right-hand side to get our final mean temperature profile in equation 5.4. By checking the mean temperature profile, it noticed it change exponentially over the tube lengths. E. We will use example 7 to show how to do the derivation on heat rate equation for constant surface temperature thermal boundary condition. 1. For constant surface temperature condition at outlet x equals L, equation 1 relates the mean temperature with the tube length. Our goal is to find the convection heat rate over the whole side surface of the tube. 2. We define the temperature difference, delta TO and delta TI, as well as side surface area AS. 3. We do replacement in equation 1. We replace temperature difference with delta TI, temperature difference with delta TO, and PL with AS, the surface area, and then solve for m dot Cp, mass flow rate times specific heat. 4. We add 0, Ts minus Ts, into the temperature difference, then combine Ts minus Tmi, which gives delta Ti, combine Ts and Tmo, which gives delta To. 5. We have convection heat rate equation 5, which is available at any condition. Next, we do replacement in equation 5. We replace m dot Cp with this term, temperature difference with this term. And next, in equation 6, we combine the numerator and denominator and define as log mean temperature difference, delta TLM. And finally, we get the convection heat rate for constant surface temperature. The rest of derivation for mean temperature and heat rate under different thermal boundary conditions will be left to students' practice. At this point, we covered topic 6. You're expected to be able to derive the heat rate and mean temperature profile equations under different thermal boundary conditions. See you next time.